Reality is not what it seems. The Journey to Quantum Gravity, by Carlo Rovelli. Introduction. Imagine, for a moment, a man boarding a ship. The year is 450 BCE. He is sailing from a bustling Greek city called Miletus, a hub of commerce and radical new ideas, and his destination is a distant port named Abdera. We don't know much about this man, Leucippus, but his journey would set in motion a detective story spanning more than 2,000 years. A quest to answer the single most profound question we can ask: what is the world truly made of? This ancient journey is where the physicist Carlo Rovelli begins his extraordinary book, Reality is Not What It Seems. Rovelli is not just a scientist, he is one of the founders of a leading theory in modern physics called loop quantum gravity, and he has a rare gift. He can take the most complex, mind-bending ideas about the universe and explain them with the warmth and clarity of a master storyteller. In this book, he invites us on a grand tour of human thought, from the first glimmers of scientific reasoning in ancient Greece to the dizzying frontiers of today's research. It's a journey that will challenge everything you think you know about your world. You see, the solid floor beneath your feet, the steady passage of time on your watch, the very space you move through, these things are not what they seem. They are beautiful illusions, simplifications that our minds have created to navigate a reality that is far stranger, far more granular, and far more magical than we can possibly imagine. So, my promise to you today is this: by the end of our journey together, you will see the universe in a completely new light. You will understand that reality isn't a static stage where things happen, but a shimmering, dynamic network of events. You will learn that time doesn't flow, that space is made of tiny, indivisible grains, and that the world is a place where things exist only in their relationships with other things. It's a breathtaking vision, one that has been pieced together by some of the most brilliant and rebellious minds in human history. And it all begins with that simple, ancient question: what is the fundamental stuff of the universe? Book summary. Our story begins in that vibrant ancient city of Miletus, 26 centuries ago. For millennia before this, whenever people asked where the world came from, the answers were always stories of gods, spirits, and mythical creatures. But in Miletus, a group of thinkers, led by a man named Anaximander, started doing something different. They decided to look for answers not in fantasy, but in observation and reason. They understood that the world could be comprehended. This was the birth of scientific thought. It was this spirit of inquiry that drove Leucippus on his voyage. When he arrived in Abdera, he and his brilliant young student, Democritus, proposed a stunningly simple and powerful idea. The entire universe is made of just two things: empty space, a boundless void, and an infinite number of tiny, indivisible particles moving within it, which they called atoms. Everything we see, they argued, the sea, the stars, our bodies, even our thoughts, is just a different combination of these atoms. As Democritus beautifully put it, just as comedies and tragedies can be written with the same few letters of the alphabet, the endless variety of the world is created by the endless combination of atoms. It was a vision of breathtaking simplicity. But it raised a deep, troubling question that would haunt thinkers for centuries. Imagine, Democritus argued, that matter was not made of atoms. Imagine it was perfectly continuous, something you could divide forever. If you were to break a piece of matter in half, and in half again, and again, an infinite number of times, what would be left? You couldn't be left with tiny pieces, because that would mean you hadn't divided it infinitely. You would have to be left with points that have no size at all. But how can you build something with size by putting together points that have no size? You can't. Therefore, Democritus concluded, the division must stop somewhere. There must be a smallest, indivisible piece, the atom. This problem of the continuous versus the granular, the smooth versus the chunky, was famously captured in a paradox by a philosopher named Zeno. Imagine the swift hero Achilles in a race against a slow tortoise. The tortoise gets a head start. To catch up, Achilles must first reach the point where the tortoise started. But in the time it takes him to do that, the tortoise has moved a little further ahead. Now Achilles must cover that new, smaller distance. And in that time, the tortoise moves a little further still. This goes on forever. Zeno argued that, logically, Achilles could never catch the tortoise, because he would have to cover an infinite number of small distances. Of course, we know Achilles wins the race. So where is the flaw in the logic? Leucippus and Democritus offered a radical solution. Maybe you can't divide space and time forever. Maybe there is a smallest possible distance, a smallest possible moment. Maybe the world, at its core, is not smooth, but granular. For over 2,000 years, this idea of atoms was just a philosophical speculation. It was brilliant, but there was no proof. Then, in 1905, a rebellious 25-year-old working in a patent office in Switzerland provided that proof. His name was Albert Einstein. He noticed that tiny grains of pollen suspended in water seemed to dance and tremble for no reason. This phenomenon, called Brownian motion, had been observed before, but no one understood it. Einstein realized that the pollen was being jostled around by invisible, microscopic particles, the molecules of the water. If the water were perfectly smooth and continuous, the pushes from all sides would cancel out perfectly, and the pollen would stay still. But because the water was made of a finite number of tiny atoms, the collisions were never perfectly balanced. By analyzing this random dance, Einstein was able, for the first time, to calculate the actual size of atoms. After 23 centuries, Democritus was vindicated. Matter is granular. This confirmation set the stage for the first of the two great revolutions in 20th century physics. But before Einstein would turn our world upside down, another critical piece of the puzzle had to fall into place. For centuries, the world of physics was dominated by one man, Isaac Newton. Newton had taken the ideas of Democritus, a world of particles moving in a vast, empty space, and had given them mathematical power. He described a universe that ran like a perfect clock. Space was a fixed, unchanging stage, and time was a universal river flowing at the same rate for everyone. And in this clockwork universe, objects moved because of forces, like the mysterious force of gravity that reached across the emptiness of space to pull the moon toward the Earth. Newton's vision was incredibly successful. We still use his equations today to build bridges and send rockets to Mars. It seemed like he had discovered the final laws of the universe. But Newton himself was deeply troubled by his own theory. How could the Earth attract the moon without anything connecting them? He called it an absurdity and left the question for future generations to solve. The answer came from a humble, self-taught genius named Michael Faraday. Working in a London laboratory in the 1800s, Faraday was experimenting with electricity and magnetism. As he played with magnets, feeling their invisible push and pull, he began to see something new. He imagined that space was not empty at all. It was filled with invisible lines of force. He proposed that an electric charge doesn't act on another charge at a distance. Instead, it creates a disturbance in this entity diffused throughout space, and this entity then acts on the other charge. Faraday had just invented the concept of the field. A brilliant Scottish mathematician, James Clerk Maxwell, took Faraday's beautiful, intuitive vision and translated it into a set of elegant equations. And when he did, he stumbled upon one of the greatest discoveries in the history of science. Maxwell's equations predicted that waves could travel through this electromagnetic field. He calculated the speed of these waves, and the result was astonishing. It was exactly the speed of light. In that moment, he understood. Light is a wave in the electromagnetic field. The vibrant colors we see are just different frequencies of this wave's vibration. We don't see Faraday's lines, we see them vibrating. The Newtonian world of empty space was gone. Reality was now made of two things: particles and fields. This discovery set the stage for the true revolution, and at its center was that same young man from the patent office, Albert Einstein. Einstein realized there was a deep conflict between Newton's physics and Maxwell's new theory of light. According to Newton, speed is always relative. If you're on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, someone standing on the ground sees the ball moving at 60 miles per hour. But Maxwell's equation said that the speed of light is constant. It doesn't matter how fast you're moving, you will always measure the speed of light to be the same. This seemed like a complete paradox. For 10 years, Einstein obsessed over this problem. And the solution he came up with, in 1905, forever changed our understanding of space and time. This was his theory of special relativity. Einstein's profound insight was that space and time are not separate and absolute, as Newton believed. They are interwoven into a single fabric, spacetime, and this fabric can be stretched and distorted. One of the strangest consequences of this is that the idea of now is not universal. Imagine you have a friend on Mars. On Earth, we have a clear idea of the past, the present, and the future. But Einstein discovered that for your friend on Mars, there's an intermediate zone. Because it takes time for light and information to travel between you, there's a period of about 15 minutes on Mars that is neither in your past nor in your future. It's an extended present. This means that the concept of a single, universal now that applies to the entire cosmos is an illusion. It's an illusion created by the fact that here, on Earth, this intermediate zone is so incredibly tiny, just a few nanoseconds, that we can't perceive it. The fusion of space and time into spacetime had another, even more world-changing consequence. Just as space and time were two facets of one thing, Einstein realized that energy and mass were also two facets of the same entity. They could be converted into one another, according to the most famous equation in all of science, $E equals mc squared $. Because the speed of light, $c$, is such an enormous number, this equation tells us that a tiny amount of mass can be converted into a tremendous amount of energy. With this single line of mathematics, Einstein had unlocked the power of the atom and ushered humanity into the nuclear age. But Einstein wasn't finished. He knew his theory was incomplete. It worked beautifully, but it didn't include Newton's mysterious force of gravity. So he set out on another 10-year journey of intense thought, a quest to understand the true nature of gravity. And the theory he produced in 1915, the general theory of relativity, is often called the most beautiful of theories. Einstein's genius was to connect two seemingly separate problems. The first was how to describe gravity. Following Faraday, he guessed it must be a field. But the second problem was deeper. What is space? For Newton, it was just an empty, rigid container. But that seemed strange. What is this container made of? And then came the lightning strike of genius. What if, Einstein thought, the gravitational field and space are the same thing? What if space isn't an empty stage, but a dynamic, physical entity that can bend, stretch, and warp? This was the core idea of general relativity. In this new picture, the sun doesn't pull the Earth with a mysterious, invisible force. Instead, the sun, because of its immense mass, creates a deep curve in the fabric of space-time around it. The Earth isn't being pulled, it's simply following a straight line through this curved space, like a marble rolling around the inside of a funnel. Gravity is not a force, it is the curvature of space-time. This beautiful and radical idea led to a series of predictions that seemed like science fiction. It predicted that starlight would bend as it passed by the sun, which was confirmed in 1919. It predicted that time itself runs slower closer to a massive object. A clock on the floor literally ticks slower than a clock on a table, an effect so real that our GPS satellites have to correct for it every day. It predicted that when a massive star dies, it can collapse under its own weight and warp space-time so intensely that it tears a hole in reality, a black hole. And it predicted that the entire universe is expanding, born from a single, incredibly hot and dense point 14 billion years ago, the Big Bang. One by one, every single one of these seemingly mad predictions has been proven true. Einstein had redrawn the cosmos. Newton's rigid stage was gone, replaced by a dynamic, flexible mollusk, as Einstein called it. The world was no longer particles and fields in space and time. Space and time were now part of the fields themselves. But even as Einstein was completing his masterpiece, the seeds of the second great revolution were already sprouting. And this one was so strange that even Einstein himself would refuse to accept it. This was the birth of quantum mechanics. It began, as great ideas often do, with a small, stubborn puzzle. Physicists in the early 1900s were studying how hot objects radiate energy. To explain the experimental data, a German physicist named Max Planck had to resort to a strange mathematical trick. He assumed that energy was not emitted continuously, but in tiny, discrete packets, which he called quanta. He thought it was just a clever calculation tool, with no real meaning. But 5 years later, in one of his other 1905 papers, Einstein showed that these quanta were real. He used the idea to explain the photoelectric effect, where light hitting a metal surface can kick out electrons. He argued that light itself is made of tiny particles, or packets of energy, which we now call photons. The granularity that Democritus had dreamed of was back, but now it applied not just to matter, but to energy and light itself. This discovery opened the floodgates. The Danish physicist Niels Bohr applied the idea of quanta to the atom. He proposed that electrons could not just orbit the nucleus at any distance, but only on specific, allowed orbits, with specific energy levels. They could jump from one orbit to another, but they could never be in between. These were the famous quantum leaps. This was bizarre, but it worked. It perfectly explained the colors of light emitted by different elements. But why? What did it all mean? The key insight came from another young German genius, Werner Heisenberg, who was just 25 years old. One night, walking through a dimly lit park in Copenhagen, he watched a figure appear under one street lamp, vanish into the darkness, and then reappear under the next. He thought to himself, of course the man didn't actually disappear in between. He's a large object, and I can easily imagine his path through the dark. But then a radical thought struck him. What if tiny objects, like electrons, do disappear? What if an electron doesn't have a position at all when we're not looking at it? What if it only materializes, only becomes real, at the moment it interacts with something else? This was the mind-shattering core of quantum mechanics. An electron isn't a tiny billiard ball following a path. It's a cloud of possibilities. When you're not interacting with it, it doesn't exist in any one place. It only appears at a specific location when it collides with something, and where it appears is governed by pure chance. The theory can't predict with certainty where the electron will be. It can only tell you the probability of finding it here or there. This led to the third key feature of the quantum world. Reality is relational. Things do not have properties in and of themselves. An electron doesn't have a position. It only acquires a position in relation to the thing that measures it. The properties of the world are not written on things, but in their interactions. The world, at its most fundamental level, is not a world of objects. It is a world of events. As the theory developed, physicists realized that this strange quantum behavior applied to everything. Not just electrons, but fields too. The electromagnetic field, which Maxwell saw as a smooth, continuous wave, was also made of discrete quanta. Photons and particles, like electrons, were also quanta of their own fields, spreading out like waves of probability. The old distinction between particles and fields vanished. The world, it seemed, was made of just one type of entity, the quantum field. So by the mid-20th century, physics had given us two spectacularly successful, yet profoundly contradictory, pictures of reality. On one hand, there was Einstein's general relativity, a world of smooth, curved spacetime, where everything is continuous and determined. On the other, there was quantum mechanics, a world of flat space, where everything is granular, probabilistic, and only becomes real through interaction. You can see the problem. A student learning relativity in the morning and quantum mechanics in the afternoon would think her professors hadn't spoken to each other in a century. This conflict is the central, unsolved problem of fundamental physics. This is the search for a theory of quantum gravity. This is where Carlo Rovelli and his life's work, loop quantum gravity, enter the story. The central idea of loop theory is breathtakingly simple, and it follows directly from the two great theories we've just explored. Let's follow the logic. Einstein taught us that space is not a background. It is a physical field, the gravitational field. Quantum mechanics taught us that all physical fields are made of quanta. They are granular at a very small scale. If you put these two ideas together, the conclusion is inescapable. Space itself must be made of quanta. It must be granular. There must be atoms of space. Loop quantum gravity describes this granular space with a beautiful mathematical structure called a spin network. Imagine a web made of nodes and links. The nodes are the elementary quanta of volume, the smallest possible specks of space. The links don't represent distance. They simply tell us which nodes are adjacent to which other nodes. This network isn't in space. This network is space. The very fabric of reality is woven from these finite, discrete relationships. This means there is a minimum possible size, a minimum volume, known as the Planck scale. It is a scale so fantastically small that if you were to magnify a single atom to the size of the entire observable universe, the Planck scale would still be smaller than a tree. Below this scale, the very concept of space breaks down. Zeno's paradox is finally, physically resolved. Achilles doesn't have to cover an infinite number of distances, because infinitely small distances do not exist. But what about time? Einstein taught us that space and time are inseparable. If space is a quantum network, what happens to time? This is where the theory takes its most radical leap. In the fundamental equations of loop quantum gravity, the variable for time? The letter T that has been in every equation of physics since Galileo simply vanishes. This does not mean that nothing happens. On the contrary, it means that change is fundamental, but it's not a change that happens in time. At the fundamental level, there is no master clock, no universal river of time. The world is a dance of elementary events, a constant transformation of these spin networks. The theory describes these transformations using objects called spin foams. A spin foam is a history of a spin network, a sequence of quantum events where the grains of space interact, combine, and separate. So where does our familiar sense of a flowing time come from? Rovelli suggests it is an emergent property, much like heat. A single molecule doesn't have a temperature. Temperature is just the average motion of many molecules. In the same way, time might be an effect that emerges only at our macroscopic scale, a result of our blurred vision of this incredibly complex dance of quantum events. Time, in this view, is a form of ignorance. It is born from the fact that we can't see the individual quantum events, only their statistical average behavior. This radical new picture of reality has profound implications. It suggests that the Big Bang was not a beginning from an infinitely dense point, a singularity. Because space has a minimum size, the universe could not have been squeezed into a point. Instead, the theory suggests it was a big bounce. Our expanding universe may have emerged from the collapse of a previous universe, which reached the minimum possible size and then rebounded outward. It also changes our picture of black holes. The singularity that general relativity predicts at the center of a black hole also disappears. Instead, matter is squeezed to an incredible but finite density, and then, due to quantum pressure, it bounces. But because time near a black hole is so distorted, this bounce, which might be very fast for the matter itself, could take billions of years from our perspective on the outside. This opens the mind-boggling possibility that black holes are not eternal prisons, but that they eventually explode, releasing what fell inside. Ultimately, the journey from Democritus to quantum gravity leads us to a new, simplified, and deeply strange vision of the world. The old ingredients, space, time, particles, and fields, have all dissolved. What remains is a single substance, covariant quantum fields. These fields are not in space or time. They generate space and time through their ceaseless, probabilistic, relational dance. The world is nothing but a swarm of elementary events, a foaming of spin foams, a network of relationships. Commentary. So, what do we do with a vision of reality this strange, this far removed from our everyday experience? What is the lesson for us, living here on this seemingly solid earth, in this seemingly steady flow of time? The most powerful lesson in Carlo Rovelli's work, I believe, is a profound sense of humility and wonder. He shows us that the world as we perceive it is not the world as it is. Our senses, our intuition, our common sense, these are tools that evolution has given us to survive on the surface of our planet. They are incredibly effective for finding food and avoiding predators, but they give us a deeply limited, parochial view of reality. They show us a flat earth, a stationary world, a universal now. And all of it is wrong. Science, Rovelli shows us, is the process of systematically questioning these intuitions. It is the art of learning to see further than our senses allow. The story of physics is a story of one veil after another being lifted. Anaximander showed us that the sky continues beneath our feet. Copernicus showed us that we are hurtling through space on a spinning rock. Einstein showed us that time is not universal. And quantum mechanics shows us that reality itself is a ghostly dance of probabilities. With each new discovery, the world becomes stranger, but it also becomes more beautiful. There is an elegance in the idea that the universe is woven from a simple set of rules, that the complexity we see is born from the endless combination of a few fundamental ingredients. Democritus's alphabet has become the shimmering, interacting quantum fields that write the epic poem of the cosmos. For a young person standing at the beginning of their life, this has a practical, and I would say, spiritual significance. It teaches us not to trust blindly in what seems obvious. It teaches us that our most deeply held beliefs about the world might be wrong. And this isn't a reason for despair. It is the very source of progress. Science, Rovelli reminds us, is not nourished by certainty. It is nourished by a radical distrust in certainty. So, how can you apply this? You can start by cultivating your own sense of wonder. Look at the world around you and remember the hidden reality beneath the surface. When you look at a sunbeam slanting through a window, remember that it is a shower of individual photons, quanta of light that have traveled millions of miles to reach you. When you feel the solid weight of a stone in your hand, remember that it is a monotonous process, a temporary configuration in a ceaseless vibration of quantum events. And when you feel the inexorable passage of time, remember that it may be nothing more than an emergent illusion, a measure of your own ignorance of the world's microscopic dance. Embrace uncertainty. The world is full of people who claim to have all the answers, but the greatest minds in history, from Socrates to Einstein, were defined by their acute awareness of their own ignorance. True wisdom is not knowing everything. It is knowing what you do not know. This is the engine of discovery. It's the curiosity that drives us to look over the next hill, to ask the next question, and to continue this magnificent, 2,000-year-old journey of understanding that began on a ship sailing from Miletus. The universe is not just stranger than we imagine, it is stranger than we can imagine. And the exploration of that mystery is one of the most beautiful adventures we can have. That was a summary of Reality is Not What It Seems by Carlo Rovelli. We've explored the grandest ideas from this incredible book today, but I'll be honest with you, a summary can only ever be a map. The real treasure is found on the journey itself. The magic happens when you read the book, when Rovelli's elegant prose and beautiful analogies click into place in your own mind, and you feel that sense of awe as a new understanding of the world dawns on you. This podcast is a doorway. If any of the ideas we've discussed today, the grains of space, the end of time, the great big bounce, have sparked your curiosity, I wholeheartedly encourage you to step through it. Grab a copy of the book, because reading it isn't just about learning facts, it's an experience that can fundamentally change the way you see your place in the cosmos. You can find a link to the book in the description below. Also, if this journey into the nature of reality has been valuable to you, please take a moment to hit that like button and subscribe to our channel, Billionaire's Bookshelf. That way, you won't miss our next exploration into another book that has the power to change your life. Let's keep learning and growing together.